farmer has 1,944 feet of fencing available to enclose a rectangular area bordering a river. No fencing is required along the river. Let X represent the length of the fence that is parallel to the river. Complete parts A through C. I've got part A here and part B and C a little bit lower. But let's pause because we've been given a picture to go along with this question. We have a river. You can make that a nice blue. We've got a river, and we're going to be building this rectangular enclosure. And no fencing is required along the river, so we're only going to be placing fencing along these three sides. We're also given the value of our, not the value of our variable, but what our variable represents. We're going to let X represent the length that is parallel to the river. So that is this side here, and they've labeled it for us with X. And in part A, we want to create a function that represents area. And the variable that is used in that function is X, the side that is running parallel to the river. So they're forcing which variable, which side we're going to use as the variable and what variable will be used in the function. So if I've got a rectangle, we know that the area of a rectangle is the length times the width. And we've got one side of that rectangle already labeled as X. So I'm going to say that that is the length. But we don't have the side that is running perpendicular to the river labeled. And what we're going to do is use the other information in the problem to come up with a representation of that other side. So I'm going to use this piece of information here that we have 1,944 feet of fencing. And we're going to use all of that fencing because we're trying to create the most area. So if we have 1,944 feet of fencing, and this side here, let's call this Y, we know that we're going to put fencing on those three sides. So I have two Y's and one X. And I want to solve for that Y. So I'll subtract X on both sides. That's 1,944 is forgot the minus X. Minus X equals 2Y. And then I'm going to divide both sides by 2. And that gives Y equals, let's see if we can divide 1,944 divided by 2. That's 972. Minus 1/2 X. So I'm able to label this side now. Instead of Y, we're able to label it with 972 minus 1/2 X. So when we're finding the area, we now have X times, that's the length, times the width, times 972 minus 1/2 X. If I use a distributive property, that gives 972x minus 1/2 x squared. And I usually like to write this in descending order, so I'll write this as 1/2 x squared plus 972x. So this is giving us a function that represents area, and the variable in that is x, which is the side that is parallel to the river. So we've created that area function. So let's move on to the next part. The next part wants us to find the dimensions that will maximize the area. Now we have our area function. A of x equals negative 1/2 x squared plus 972 x. And we notice that that area function is a quadratic. We know something about the graph of quadratic, that is a parabola. Not only that, but our leading coefficient, negative 1/2, is negative, and anytime the leading coefficient is negative, our parabola is a down-facing parabola. And we're looking for the maximum. The maximum is going to be this highest point, which is the vertex. So the max will occur at the vertex. So that's our strategy for finding the maximum area, and finding the dimensions of that maximum area is to find the vertex of our quadratic, which is the area function. Now we have a vertex formula, and the vertex formula, the x-coordinate will be negative b over 2a, and a is our coefficient of the squared term, and b is the coefficient of our x term. So we get, in solving this vertex formula, negative b, that's negative 972, over 2 times negative 1/2. So this works out to be a negative 972 over negative 1, because those 2's cancel, which is a positive 972. So going back to our picture for a moment, what we've just found is this x here, which is the side parallel to the river. And our side perpendicular to the river is written in terms of x, so I'm able to find that as well. So remember right here, y, this side that is perpendicular to the river, is 972 minus 1/2 x. So let's work that out. So y, that's 972 minus 1/2 times 972. That's 972 minus, let's see, what is half of 972? That's 486. And 972 minus 486 is 486. So this gives us the dimensions of the rectangle. So we're going to have the side that is parallel to the river. I think I spelled that wrong. 1 R, 2 L's. So parallel to the river will be 972 feet, and perpendicular to the river will be 486 feet. So in our final part, we need to know what is this maximum area, and remember that area is length times width, and we have the length and the width here. We can do 972 times 486, and 972 times 486 will give us 472,392, but since we did feet times feet, this will be feet squared. So 472,392 square feet is the maximum area. Amy, the owner of Amy's Pottery, can produce china pitchers at a cost of $4 each. She estimates the price function to be P equals 18 minus 3x, where P is the price at which exactly X pitchers will be sold per week. Find the number of pitchers that she would produce and the price that she should charge in order to maximize the profit. Also find the maximum profit. So on this question, we have quite a bit of work to do before we can get to the profit function. So there are some business formulas that we need to be aware of so that we can get to that profit function. So for the profit function, we know that the profit is the revenue minus the cost. And we also have formulas for building the revenue function. The revenue function is X times P, which is the number of units times the price. And the cost is the number of units times the cost per unit. I don't have a variable for that. So let's say that the cost per unit is a lowercase c. This capital C is the cost for all of the units. The lowercase c is the cost per. And we are given the cost per unit, which is right here. So in order to get to that profit function, I first need to find the revenue function, then I need to find the cost function, and then I'll subtract those in order to get the profit function. So let's start with the revenue function. So for revenue, we're going to use X times P. And we're given this right here, the price function, P equals 18 minus 3x. So I can replace that P with 18 minus 3x. And then I'll use the distributive property that will be 18x minus 3x squared. So that's our revenue function. We can write that as negative 3x squared plus 18x. So then I need the cost function. And the cost function will be that lowercase c times x. We've got 4, it costs $4 to produce times how many that we produce, so we get 4x. And now that we have both the revenue and the cost function, we can find profit. So profit is revenue minus cost. We have a revenue of negative 3x squared plus 18x minus a cost of 4x. So that's negative 3x squared, and we'll combine those like terms. 18x minus 4x is 14x. So we have our profit function. So if we take a look, we want to find, there are many parts here, we want to find how many pitchers we should produce and the price in order to maximize the profit, and we also want to find the maximum profit. So because we're trying to maximize the profit, we're going to take a look at this function. This is the profit function, and we notice that it is a quadratic. And a quadratic has the graph of a parabola. And this parabola has a leading coefficient a of negative 3. And because it's negative, we know that it's a down-facing parabola. That's very helpful for us because we're looking for the maximum. And the maximum is this highest point here, and that max is at the vertex. So if we're able to find the vertex, we're going to be able to find the that maximum profit. So we do have a vertex formula, and the vertex formula is H is equal to negative b over 2a. For our problem, a is negative 3 and b is 14. So we have a negative 14 over 2 times negative 3. And this is negative 14 over negative 6. And that reduces down to 7 over 3. Okay, so this is going to give us a decimal value, but we're going to round to the nearest whole number. So 3 will go into 7 2 and a third times, so that's going to round to 2. So this is going to be like 2.3 repeating, but we're going to round it to the nearest whole number. And that's going to give us X. So X is the number of pitchers sold per week, which is also how many pitchers she should produce. We also want to know the price. So the price that she should charge, that will be, this is the lowercase p. So we're going to use this right here, 18 minus 3x. That's 18 minus 3 times 2. 18 minus 6 would give 12. She should charge $12. And we also want to find the maximum profit. So this is the capital P. We'll do negative 3 times 2 squared plus 14 times 2. That's negative 3 times 4 plus 28. Negative 12 plus 28 would give 16. So we'll have a profit of $16. A maximum profit of $16. In this question, we're given a graph of a function that we're going to call f. And we're asked a bunch of questions related to the inverse of this function. So the first question that we're asked is, what is the domain of f inverse? And what we know about inverse functions is that the x and the y value get switched. So really, if we're looking for the domain of f inverse, and we're given f, we're going to use the range of f to answer this question. So because x's and y's get switched, the domain and range get switched. So I'm going to use my ruler, and we're looking for the range of f. Those are the y values. So my lowest range value or y value is negative 5. So my range of f starts at negative 5, and my highest range value or y value will be 6. So the range of f is -5 to 6, and that means that the domain of F inverse is also -5 to 6. So then we're asked to find, on the next part, what is the range of F inverse. So as we just said, the domain and range get switched, and the range of the inverse will be the same as the domain of F. So let me take my ruler, hold it vertically, and now we're going to be finding the x values, the domain of F. So that starts at -6. So my domain of F starts at -6 and continues all the way until 4. So we have a domain of F being from -6 to 4, which is the same thing as the range of F inverse. And the next thing that we're looking for is the y-intercept of the inverse. So typically when we're looking for a y-intercept, we let x equal 0. However, remember that our graph represents F, but we're really interested in the inverse. The x and the y get switched, so we really want to find when y is equal to 0. So y is equal to 0 right here. So just to clarify, on the graph of F, we have the ordered pair -2, 0, which is an x-intercept. With the inverse, the ordered pairs get switched. The x's become y's and the y's become x's, and that is a y-intercept of the inverse. So the y-intercept of F inverse will be at -2. So then let's take a look at the next part. This one says evaluate F inverse of 0. We want to find F inverse of 0. So on the inverse, our ordered pair would be 0, comma, and we don't know what that y part is. But on F, the x's and y's get switched, so we don't know the x part, but we know the y part being 0. So if I were to use more formal notation for what I'm doing here, if I'm looking for F inverse of 0, I know that F of something equals 0. So I'm looking for a y-coordinate of 0. And that's going to occur right here. This ordered pair has an x of 1 and a y of 0. So F of 1 equals 0. I'm sorry, I've stated that incorrectly, so let me correct myself. So that does not have a y-coordinate of 0, that has an x-coordinate of 0. So we're going back to this spot right here. This spot has y of 0 and an x of -2. So F of -2 equals 0. So you can see how easy it is to get confused on this. So you get F of -2 equals 0, and that is F inverse of 0 equals -2. So this one, the answer is -2. Okay, so let's try it again so we can get a little bit more clarity. So on the next one, we want to evaluate f inverse of -5. Okay, so let's do that over here. F inverse of -5. We're not sure what the answer is, but it's going to produce an ordered pair, -5 and something that we don't know. Let's leave it as a question mark. Now with f and its inverse, the x's and y's get switched. So with f, we'll have a question mark on the x part, but we'll know the y part to be -5. So on my graph of f here, I'm looking for a y value of -5. So right here we have a y coordinate of -5 and an x coordinate of -6. So we know that f of -6 is equal to -5, and f inverse of -5 is -6. So the answer to this one would be -6. But then we have our next part, f inverse of 6. Let's do it in a different color because my work is getting a little jumbled here. We're finding f inverse of 6. We don't know the answer. So for the inverse, we would have the ordered pair 6, comma, something we don't know. But for f, it would be f of that number we don't know equals 6. So we're looking for a y coordinate of 6. Right here is a y coordinate of 6. That ordered pair is 4, 6. So we know that f of 4 equals 6. And f inverse of 6 equals 4. So we get an answer of 4 for part F. F inverse of 6 equals 4. Okay, so let's do the last one. We'll do it in green. So we have f inverse of 1 equals something we don't know. That would give an ordered pair 1 question mark. F of that question mark should equal 1. So that 1 becomes the y coordinate. So having a y coordinate of 1 will be right here, and that ordered pair is 0, 1. So f of 0 equals 1, f inverse of 1 equals 0. So f inverse of 1 equals 0. So let me zoom out so we can see all those parts. And the main thing to keep in mind is that with inverses, the x's and y's get switched, the domain and range get switched. The function g of x is equal to that's a 3x minus 8 over 7 minus x is 1-to-1. We have a 1-to-1 function. We want to find the inverse of g, state the domain and range of g, and state the domain and range of g inverse. So let's start by finding the inverse of g. There's a 3-step process that we can go through to find the inverse. We have g of x equals 3x minus 8 over 7 minus x. And the first thing I'm going to do is change this g of x to y. Now the reason why I'm doing that is really just to make our symbols a little bit easier to work with. G of x is four different symbols there, y is just 1, so it's less for us to write. The next thing we're going to do is what is going to help us produce the inverse of G. With inverses, the x's and y's are switched, and so we're going to switch the location of our x's and y's in our equation. So we're going to have, instead of a y here, we're going to have an x, and then 3y minus 8 over 7 minus y. So this y became an x, these x's became a y. And the final step, which is going to take the longest, is to solve for y. So we want to rewrite this equation as y equals. So we need to solve for that y. So let's work on that. So this is looking a little bit messy at the moment because we have multiple y's in our equation and the y is in the denominator. So first I'm going to address the issue of the y in the denominator by clearing fractions. We're going to multiply both sides by 7 minus y. So on the left I have x, and I'm going to multiply that by 7 minus y. And on the right I have 3y minus 8 over 7 minus y, and I'll multiply that by 7 minus y. Now on the right, this clears the fractions, so it cancels out the fraction on the right, leaving me with 3y minus 8. And on the left, I'll use the distributive property, and that gives 7x minus xy. So now I've gotten rid of the y in the denominator, and now I need to fix the other issue of having multiple y's. So I want to collect all the y's to one side of the equation, and everything that is not a y, every term that doesn't have y, onto the other side. So I'm going to move this term over here so that all the y's are on the same side, and I'm going to move this term over here so that every term that doesn't have y is on the other side. So that will give negative xy minus 3y equals, oh, I don't like how this is going with all these negatives, so I'm going to switch it up. So here's what I'm going to do. Instead, I'm going to move this term with y to the right, and I'll move this term that doesn't have y to the left. So all the y's will be on the right, and all the terms that don't have y will be on the left. So that will give 7x plus 8 equals 3y plus xy. So now that I have collected the y terms, I'm able to factor out the y. And when you factor it out, you now only have one y. Now I can solve for y, and I'll divide by 3 plus x on both sides. That gives y equals 7x plus 8 over 3 plus x. And now that we've solved for y, we now know the inverse. So our original function was g. Our inverse is g inverse of x. That's 7x plus 8 over 3 plus x. So we now know the inverse. I'm going to zoom back out so that we can see the other parts of our question. So the other parts of our question say, state the domain and range. So we want the domain and range of G and the domain and range of G inverse. Now we have some strategies from previous chapters for finding domain. So let's write down our two functions. We have g of x equal 3x minus 8 over 7 minus x, and we have g inverse of x equaling 7x plus 8 over 3 plus x. And we're looking for the domain of each one of these functions. They're both rational functions. So if I set the denominators equal to 0, I'm going to find the domain. So for the g, I'll set 7 minus x equals 0. Add x on both sides. That gives 7 equals x. So we know that 7 is a restricted value. It will cause the denominator to be 0 and the function to be undefined. So the domain will be all real numbers except for 7. So the domain of g will be negative infinity to 7, union with 7 to infinity. That's all real numbers except for 7. For g inverse, I'll set that denominator equal to 0. Subtract 3 and get x equals negative 3. Negative 3 is our restricted value for g inverse. So its domain will be all real numbers except for negative 3. The domain of g inverse will be negative infinity to negative 3, union with negative 3 to infinity. So as we've said earlier, the x's and y's get switched. So the domain and range get switched. So now that I know the domain of both, I can know the range of both. The range of g is the domain of g inverse. So that's negative infinity to negative 3, union with negative 3 to infinity. The range of g inverse is negative infinity to 7, union with 7 to infinity. So our strategy for finding the range is that we use the domain of the inverse. So we now have our inverse function, which is right here, 7x plus 8 over 3 plus x, and we have the domain and range of g and the domain and range of g inverse. Find the function f composed with h and simplify. We're given f of x to equal 11x plus 13 and h of x to equal square root of x plus 3. So we want to find f composed with h. We have to know what that operation means. F composed with h of x is the operation that substitutes one function inside of another function. So we have h being our inside function and f being our outside function. So the function that is before the composition symbol is our outside function, and the one that is after our symbol is the inside function. So we have f of h of x. So we want to substitute h of x inside of f. So h of x is square root of x plus 3. And we're going to put that in place. The square root of x plus 3 will be substituted in f. It goes in the spot where x is. So this becomes 11 times the square root of x plus 3 plus 13. We can write that as 11 square root of x plus 3 plus 13. And there's not really any simplification that we can do here, so we'll stop. For the given rational function, answer parts A through C. we have the function f of x equals x over x squared minus 4. We want to find the domain, the y-intercept, and the x-intercepts. So let's start off with the domain. This is a rational function, and with a rational function, we need to pay attention to the expression in the denominator. Now, the reason we focus on that is because a rational function is undefined when we have a 0 in the denominator. So we want to figure out when that denominator, x squared minus 4, equals 0, and that will give us our restricted values. So I can add 4 to both sides, and that gives x squared equals 4. I can square root both sides, and that gives x equals plus or minus 2. These are our restricted values. All other real numbers will be a part of our domain. So if we think of that on the number line, we're saying that -2 and +2 are not part of the domain, and every other real number is a part of the domain. So we can write that domain in interval notation, -infinity to -2, union with -2 to 2, union with 2 to infinity. So that gives us our domain. Then we want to find any y-intercepts. To find a y-intercept, we let x equal 0. So we're going to substitute a 0 into our function. That gives 0 over 0 squared minus 4. That's 0 over -4, which is 0. So this function does have a y-intercept, and it's at 0, 0. Then we want to find our x-intercepts. We find x-intercepts by letting y equal 0. Now we're using function notation, so f of x is y. So we're going to set f of x equals 0. So that's 0 equals x over x squared minus 4. And we want to solve this equation. We'll solve it by clearing fractions. So I'm going to multiply both sides by x squared minus 4. 0 times x squared minus 4 is 0. And on the right-hand side, x over x squared minus 4 times x squared minus 4 will cancel out that denominator and leave you with the numerator of x. So we have an equation here, 0 equals x, that is solved. X equals 0, and we get that we have an x-intercept at 0, 0 as well. So 0, 0 is an x-intercept and a y-intercept for this function. Find all vertical asymptotes and create a rough sketch of the graph near each asymptote. F of x is equal to 1 over x minus 3. That's our function, and we want to find the vertical asymptotes for that function. So I have a process here for finding vertical asymptotes. We've got our function, p of x over q of x, and we need that to be a rational function with no common factors. And once we know that it has no common factors, we know that if we have a being a 0 of the denominator, then x equals a is a vertical asymptote of that function. So for this process, we want to make sure these first two steps are trying to guarantee that we have a rational function with no common factors. So we factor the numerator and denominator and cancel out any common factors. For this particular rational function, 1 is already completely factored, x minus 3 is completely factored, and we have no common factors. So we have no common factors. So once we've done that, then we're going to work on finding that 0 of the denominator. So we're going to set the denominator equal to 0, x minus 3 equals 0. We're going to add 3, and that gives x equals 3. So we know that this function has a vertical asymptote at x equals 3. Now, the question also states that we want to draw a sketch of what is happening near the vertical asymptote. So it's helpful if we know exactly what a vertical asymptote is. So let me bring in a definition of a vertical asymptote. So when we have a vertical asymptote, what we know is that f of x, that is y, increases or decreases without bound. What that actually means is that the y is approaching infinity, or the y is approaching negative infinity as our graph gets closer and closer to that vertical asymptote. So when we're drawing our sketch, the y is either going to approach infinity or negative infinity, and that's what we have to figure out before we draw the sketch. So our function is f of x equals 1 over x minus 3. We start to draw the sketch at x equals 3. We know that the graph will go to infinity or negative infinity. So on this right-hand side, it could go to infinity or negative infinity. We're not sure which one. And on the left-hand side, it could go to infinity or negative infinity, and we're not sure which one. So what we're going to do is we're going to test it out on each side. So we're going to pick a number that is close to 3 but bigger than 3. So maybe like 3.1. And we're going to pick a number that is close to 3 but smaller than 3, like 2.9. And when we substitute it into our function, it's going to be clear to us whether it's going to infinity or negative infinity. So if we calculate f of 2.9, we get 1 over 2.9 minus 3. And 2.9 minus 3 is a negative. We have a positive divided by a negative, and that's going to be negative. So that tells us that our y is going to approach negative infinity. So I'm going to get rid of this positive one. And then on the other side, we're going to calculate f of 3.1. That's 1 over 3.1 minus 3. 3.1 minus 3 is a positive. A positive divided by a positive is a positive. So now I know that my y is going to go to positive infinity. And let's get rid of this negative infinity. So this gives me a sketch of the graph near that asymptote. So at x equals 3, we have a vertical asymptote. To the right of 3, the y goes to infinity. To the left of 3, the y goes to negative infinity. For this one, we want to know, is the function with the graph one-to-one? So we're given this picture, and we want to know whether it represents a one-to-one function. So I've copied here the definition of one-to-one. A function f is one-to-one if for any values a not equal to b in the domain of f of a is not equal to f of b. So if we simplify the meaning of this definition, this is saying x is not equal to A is not equal to B, that's saying that the x's are different. And then over here we have f of A not equal to f of B. This is saying that the y's are different. And on this function, we can come up with what we call a counterexample to this definition. So if we take a look, say for instance right here, this is a situation when these two y values are the same at these 2 points. They have a y value of 3. However, the x's are different. So here it says if the x's are different, then we have the y's different. Here we have the y's being the same and the x's are different. So if the x's are different, we should have all the y's being different, and that is 1 to 1. So in this example, we don't have a 1-to-1 function because it's not following the definition of the x's being different than the y's being different. Here we have x's that are different and the y's being the same. Now we do have a strategy that we typically use to decide whether the graph represents a 1-to-1 function. And what we use is something called the horizontal line test. So when you have a graph and you're trying to decide if it's a 1-to-1 function, you're going to draw horizontal lines all over the graph. And what you want to pay attention to are the intersection points of your horizontal line. So we'll notice that this has one intersection point, but all of these ones down here have 2 intersection points. So when we get 2 or more intersection points, this is an indication that the function is not 1-to-1. And because you have a horizontal line, horizontal lines have all the same y values. So what you're getting with a horizontal line is y values that are the same. And so when you get 2 intersection points, you're getting 2 points that have the same y value. So y's that are the same, x's that are different, and that is a violation of the definition of 1-to-1. So this particular function is not 1-to-1. Now if you draw horizontal lines and you only get 1 intersection point or no intersection points all over the graph, then you can say that it is a 1-to-1 function. The function f of x is equal to 1/6 x minus 2 is 1-to-1. We want to find the inverse of f and state the domain and range of f. We also want to state the domain and range of f inverse. So we know that this function is 1-to-1, and that tells us that the inverse will also be a function. So let's find the inverse, and we're going to use a 3-step process for finding the inverse. We have f of x equals 1/6 x minus 2. And our first step is we're going to change that f of x to y. Now this step just makes the equation a little bit easier to work with. And the next step is we're going to switch the x and the y. This is what's going to help us find the inverse. So our equation would be x equals 1/6 y minus 2. Inverse functions switch the x and y, so we're going to switch the x and the y to find the inverse. In the final step, we're going to solve for y. So I'm going to add 2 to both sides. That gives x plus 2 equals 1/6 y. And then I want to get rid of that 1/6, so I'm going to multiply both sides by the reciprocal, which is 6. And this gives y equals 6x plus 12 if I use the distributive property on the left, and on the right, the 6 times 1/6 becomes 1. So now we have our inverse function. F inverse of x is equal to 6x plus 12. And we found the inverse. We also want to state the domain and range of each of these functions. So let's write them down over here. We have f of x being 1/6 x minus 2, and f inverse of x is 6x plus 12. So we're trying to find the domain and range of each of these functions. And when I take a look at them, I have a strategy for finding the domain. This is a linear function because we have x to the first power. A linear function is a type of polynomial. And polynomial functions have no restrictions on their domain. So I know that the domain of f is all real numbers, negative infinity to infinity. When I look at f inverse, I also see a linear function, which is a type of polynomial. So it also has a domain of all real numbers, negative infinity to infinity. And as we said earlier, inverses switch the x and y values. So the x's and the y's, the domain and range, also get switched. So if I'm looking for the range, if I'm looking for the range of f, I'm going to use the domain of the inverse because, remember, those x's and y's get switched. So the range of f is negative infinity to infinity. And then if I'm looking for the range of f inverse, I'm going to use the domain of f. That's going to be negative infinity to infinity. So I've found the inverse, and I've also found the domain and range of each one of these functions. Use the graph shown to find the following: the domain and range of the function, the intercepts, if any, horizontal asymptotes, vertical asymptotes, oblique asymptotes. So in this question, it's going to be quick to identify the intercepts, the asymptotes. So let's do those first, and then we'll come back and do the domain and range. Now this graph has been nice enough to identify the asymptotes with these vertical and horizontal dashed lines. But I'm going to take a little bit more detailed approach, thinking about the definition of what these different asymptotes are. So if I'm starting with the horizontal asymptote, the definition of a horizontal asymptote is that as x is approaching infinity or x is approaching negative infinity, then y will be approaching a certain number. So if I'm looking for horizontal asymptotes, I should be looking at when x is approaching infinity and negative infinity, and that's these portions of the graph here. So if I analyze this graph in blue closely, what I can see is that x is approaching negative infinity and y is approaching this dashed line that's been drawn for us. That dashed line is occurring at -2. On the other end, x is approaching infinity and y is approaching that dashed line, which has been marked for us at -2. So by analyzing the graph, we can see that we do have a horizontal asymptote at y equals -2. So then let's think about our vertical asymptote. So for the definition of a vertical asymptote, x will be approaching a number and y will be approaching infinity or -infinity. So when you're looking for vertical asymptotes, you should be looking for y values that are approaching infinity or -infinity. So that's occurring here, here. These two y values are going to -infinity, and here these y values are going to infinity. So if we analyze it a little bit closer, x is approaching that vertical dashed line, which is occurring at -2, and we're below -2 here, and y is approaching -infinity. On this next one over here, x is approaching 2, we're now above 2, and y is approaching -infinity. And then up here, x is approaching -2, we're above 2, and y is approaching infinity. And then we have x approaching 2 from below 2, and y is approaching infinity. So if we look, we've got some in common here. Both of these are approaching -2, and both of these are approaching +2. So we have two vertical asymptotes. We have a vertical asymptote at x equals -2 and another vertical asymptote at 2. Now, the last asymptote is an oblique asymptote. An oblique asymptote is when x is approaching infinity or x is approaching -infinity, then y will approach a line ax plus b. And we've already determined that that we have a horizontal asymptote. We saw that as x approaches infinity, y was approaching a number and not a line. And so we can say that there is no oblique asymptote. Now we're also interested in finding the intercepts. Now finding the intercepts, we were looking for x-intercepts, where the graph crosses the x-axis, so that will occur here and here. And let's see if I can figure out what those numbers are. The tick marks look like we've got 1, 2, 3, 4, 5, and we're going 2 tick marks out of the 5, so this would be 1 and 2 fifths. Yeah, so this would be 1 and 2 fifths. Or we could say that's 1.4. And then -1.4 for our x-intercepts. And then for our y-intercept, that's where it crosses the y-axis. Looks like it's right on that -1. So we have x-intercepts at -1.40 and 1.40, and a y-intercept at 0, -1. So then finally we want to find the domain and range. So I'm going to use my ruler to help me find the domain. We have a domain. I'm going to hold my ruler vertically to point to the x's. So looking along this would be an arrow, so my domain would start at negative infinity. The vertical asymptote that we see here is going to be a break in the domain. So we're going to have a break in the domain at -2, but it picks up right after. We have another break in the domain at +2, and then it picks up right after. So our domain for this rational function is -infinity to -2, union with -2 to 2, union with 2 to infinity. And then we want to find the range. The range are the y values, so we're going to hold our ruler horizontally, go from bottom to top. Now these would represent arrows here, so our range will start at -infinity. And we're going to continue until we get to this horizontal asymptote. The range will take a break at that horizontal asymptote. And you can see here, let me move my ruler. I'm going to highlight it for you. So along this set of y values, if I go left to right, there are no portions of the graph that run along this section. So those y values will be not included in the range. So our y values don't start again until we get to that y-intercept at -1. And I'm going to put a bracket on that -1 to include it. And then these would be arrows. So our range would go to infinity. So our range is -infinity to -2, union with -1 to infinity, and that's including -1. Find f composed with g for the indicated functions and simplify. Our functions are f of x equals 8x plus 2 and g of x equals 7 over x plus 2. So we want to find f composed with g of x. This operation of composition is the operation of substituting one function inside of another function. So we're going to substitute g of x into f of x. G of x will get substituted in place of the x in f, and that will give us the expression 8 times 7 over x plus 2 plus 2. Now this is f composed with g of x. However, we want to simplify the answer here. So if we simplify, we'll get 56 over x plus 2 plus 2. And we want to simplify even more. So let me back up. What I did was I treated 8 like 8 over 1, and I multiplied the numerator times numerator and denominator times denominator. And I'd like to simplify a little bit more by combining this into a single fraction. So to do that, I'm going to treat 2 as 2 over 1 and get a common denominator to add these together. So the common denominator would be x plus 2, and I'll multiply by x plus 2 over x plus 2. This gives 56 over x plus 2 plus, and I'll use the distributive property on the next term, that's 2x plus 4 over x plus 2. And now we have a common denominator. and we'll combine the numerators together. That's 2x plus 60. Now we could try one more thing to simplify to see if there are any common factors to cancel out. We have a common factor in the numerator of 2. That becomes x plus 30 when we factor it out. And you can see that there aren't any common factors to cancel out here. So we have found f composed with g and also simplified our function. Thank you for checking out my videos. Have a great day.